Hello people from the future, welcome to Normalized Nerd. Today I'm gonna talk about a very important concept in all of machine learning and deep learning, which is the stochastic gradient descent. Well, actually in one of my previous videos I have talked about the vanilla gradient descent, which will be appearing in the cards right now. And in that video I actually explained how the vanilla gradient descent works and have actually written the code from scratch in Python. Now before continuing with this video, I would highly recommend you to watch that video first, because if you are new to gradient descent then that basic will be necessary here. So let's get started. Well, a quick recap of the vanilla gradient descent is this update equation. Well, this update equation simply means that we are updating our weights, the wj, by the previous weight minus learning rate times this term. Well, this term is nothing but the gradient of our cost function over all the examples. To give you a little bit context, I'm gonna show you a cost function of a binary classification. This is our binary classification model, a logistic model, and this is our cost function. And in this cost function you can see that we are summing over all the cost in each example, that is 1 to m is the size of our training set. You can easily see that in this term we are actually summing over all our training examples, then computing the gradient and then update it, then we update the weights. So suppose we have m equal to 10 million. So to update our weight for just only one time, we have to iterate through all our 10 million examples and calculate their gradients, then sum them, and then we can only update our weights, which will be an extremely computation extensive job. So we must find a better way. There has to be a better way. Well, the better way is the stochastic gradient descent. So the stochastic gradient descent goes something like this. Well, you can see that the update equation looks very similar, but in this case, instead of having this term, which is the gradient of cost over all the examples, we are calculating the gradient of cost for only one example. Then immediately we are updating the weight, and then we pass the second example, update the weight, third example, update the weight. So we are not waiting for the 10 million examples to compute their gradients and then update the weight. We are updating our weights example by example, so it is computationally much less expensive. If you are not familiar with the concept, then you must be thinking that why the hell should it work? Like, obviously we are not calculating the gradient over all the examples, we are just calculating gradient over one example and that we are updating the weight. So in some sense it shouldn't work, right? Well, actually not. Well, obviously it's not gonna work as well as the vanilla gradient descent, but we will converge to a value that is very close to the minimum in a much lesser amount of time. Now to give you an intuition that why it should work, I'm giving you an example. Suppose you have made an application and you want to test your application on 100 customers and write their feedbacks and improve your apps. Now in how many ways you can do it? Actually you can do it in two ways. In first way, you can just uh, call your 100 customer, then you give the application to the first one, then he gives some feedback, you write it down, then you pass it to the second customer, he gives some feedback, you write it down, and so on, and you complete all the 100 feedbacks from 100 customers. Then then according to those feedbacks you improve your application. But in the second way, you can do that, you are taking the feedback from the first customer, you are improving the application, then you are giving it to the second customer, taking his feedback, you are updating your app, and so on. So you can see that the second approach, you are actually improving your app in a much faster rate that you are doing in the first process. The second process is exactly what is happening in the stochastic gradient descent, and the first process is happening in the vanilla gradient descent. So I hope that little example was really intuitive and you can appreciate the why the stochastic gradient descent actually works. Now let me show you the convergences of stochastic gradient descent and vanilla gradient descent. To show you the convergence, I am actually gonna take help of something called contour plots. Well, these contour plots are actually a tool of representing higher dimensional functions on a 2D plane. The lines I am drawing here actually represents the points which have a same output in higher dimension. So suppose this axis is my x1 and this axis is my x2, and these two are features, and they are the inputs of a function, and the function, that is the cost function, will be outputting a number, say f of x1 and x2, and suppose this is plotted in 3 dimension, and these lines actually corresponds to the same height in that direction. So that simply means that if 2 points are lying on this line, then they have same output for this function in 3D. Okay, first let me draw the steps for vanilla gradient descent. So the steps may be something like this, this, and so on. And let me draw the stochastic gradient descent path. This may be something like this. You can already see that this will be way more noisy, and it may not reach the exact minimum, but it will reach to a good enough minimum in a less amount of time. Well, why? By looking at this plot, you may first think that, wait, the stochastic gradient descent is taking way more update steps than this vanilla gradient descent. Then how the hell it can be fast? Well, you should notice here that here one update takes way less amount of computation than one update in vanilla gradient descent. In this vanilla gradient descent, okay, let me just write the names here, the VGD, and this is SGD, and you can see then vanilla gradient descent, to update one step we are actually iterating over all our training examples, and which is basically called one epoch. We are updating only after one epoch is completed, but in stochastic gradient descent we are updating as soon as one example is completed. So in stochastic gradient descent we are having much more number of updates, but a much less number of epochs, and much less number of epochs means we are not iterating through the whole example a lot of time, so which basically increases the efficiency of our algorithm, and we find a minimum in a much lesser amount of time. So I hope that this plot actually gave you some more intuition about the stochastic gradient descent. Now let me tell you something about mini batch gradient descent. Well, mini batch gradient descent is something in the midway between vanilla gradient descent and stochastic gradient descent. Why so? Because in this update step you can notice that we are computing the gradient of costs over a batch. Well, what does a batch mean? Well, a batch means a fixed portion of our total training set. So suppose batch size is x, so we are taking exact x examples, we are computing the gradient of cost, and we are updating the weights. So you can see, if x is 1, then it becomes stochastic gradient descent, and if x becomes m, then it becomes vanilla gradient descent. So in a sense, mini batch gradient descent actually uses the flexibility of stochastic gradient descent and the accuracy of vanilla gradient descent. So by adjusting the batch size, we can actually get one gradient descent algorithm that works better than both vanilla gradient descent and stochastic gradient descent. And in fact, this is the mini batch gradient descent that is used in every implementation of gradient descent in every library. So let me just quickly draw the contour plot of this mini batch gradient descent for you. So this contour plot will be less noisy than stochastic gradient descent, but more noisy than vanilla gradient descent. So it may be something like this. Well, I must tell you that when you are using mini batch gradient descent, we have to take the batch size as a power of 2. Well, we do it because our machines are compatible with the memory size of powers of 2. So that's why it is better to take batch size of a power of 2, and generally 32 is regarded as the best batch size for mini batch gradient descent. So I hope the concept of stochastic gradient descent and mini batch gradient descent are clear to you. Now I'm gonna implement the code of the stochastic and mini batch gradient descent for a binary classification. Well, I have actually implemented the code in one of my previous videos called the logistic regression from scratch, which will be appearing right now in the cards. And if you haven't seen that, then I would suggest you to see that to be clear with the concept of logistic regression. Then see this portion, because now I'm not going to explain the concept of logistic regression. I'm going to focus on the implementation of stochastic gradient descent for that problem. So let me just quickly go through these things. This is my model for logistic regression, and this is our cost function, and this is our gradient of cost function. Now I'm gonna change some things here that I didn't do in that video. Let me just tell you. Now as the bias term, we are not going to use b here. Instead, we are going to do a trick, which is I'm gonna take a new variable, the x0, and it will be actually x to the power 0. Okay, and I'm gonna multiply it with something called w0. So this will be my b, and you can see that whenever I am raising x0 to the power 0, it's just becoming 1. So it is basically becoming w 0 is equal to b. So I am treating bias term as one of my weights. Well, why I am doing this? Because by doing this, I can write in my vector of weights w0, and in my training examples, I'm just gonna write x0 to the power 0, that is equal to 1 for all the entries in my first column. And by doing this, I am actually gonna write the equation of our model in just one line. Well, how can we do this? Let me just show you very quickly. We can actually write then that our model is just gonna be x dotted with w, and this dot means dot product, and obviously there will be a sigmoid term at the beginning. So this will be our model, and which will be very easy for me to code. And another thing is that if you see here the gradient of our cost function, we can actually simplify this a bit. How? That you can see that xj is in both cases. So what we can do, we can just take that common, and I can just write it as something like this. So we can multiply the vector xj. So that will make our life a lot easier while we are gonna code it. And obviously, if you don't know, I'm just reminding you once again that this y hat means prediction and y means ground truth. So I hope the conceptual part is pretty much clear to you. Now let us jump into the code section. Oh well, one thing I forgot, that you may actually use a regularization term in your cost function, and if you want to do it, you just want to add lambda and the weights here and the L2 norm, actually L2 norm square. So let me just write the formula of that L2 norm square also. So if I have W here, and I am gonna calculate the L2 norm squared, that will simply become W1 square plus W2 square plus W this one multiply, and there will be a lambda term. So you can use that if you want in your equation, but for the sake of simplicity I'm not gonna writing this term here, but obviously this is very easy to include the code I'm writing right now. Well, if you are still with me, then you should congratulate yourself because that was some intense stuff. And now, what is going to happen is the fun stuff. Well, so first we are gonna create a fake data, and to create a fake data for our binary classification, we are gonna import the scikit-learn and the sample generators and make blobs actually. So I'm gonna make two blobs. The center will be 2 here because this is a binary classification problem, and I'm gonna take 300 samples, and this is gonna create me two classes. So let me just run it, and after that I'm gonna visualize the classes that it has created for me, on which we are going to run our model. Okay, it is taking a little bit of time. Well, you can see that it has created two classes. The blue ones are 0 and the yellow ones are 1, and we are solving this problem by stochastic gradient descent and logistic regression, and and we should get a line like this after we are done with our coding. Okay, so let's get started. Okay, so first thing I'm gonna do here is to define a function which will actually gonna help me in creating the batches. Well, in my coding I am just gonna implement the mini batch gradient descent, and if you want to implement the stochastic gradient descent, you just have to set batch size is equal to 1. In this particular case I'm gonna work with batch size of 32. So after that I'm just adding ones in the first column of every row of our matrix of features, that is our matrix X. And okay, let me just run this quickly, and let me just run this also. So you can see that we have 300 examples, so the number of rows is 300 and the number of features we are having is 3. Well, 2 are actual features because here we have set n features is equal to 2. So 2 are actual features, and the third one, that is the first feature, is just gonna be ones. Well, after that, this is my logistic model. Well, this is the simple sigmoid function, and this is my model where I am just multiplying x and w. Well, remember that this is a dot product. After that I am gonna compute the cost, which is the binary cross entropy function. Well, if you are working with multiple classes, then you should be using categorical cross entropy, but in our case this is just binary cross entropy. So here comes the stochastic gradient descent, and first, before jumping into that, we need to actually compute the gradients. Now in the conceptual portion, you can see that here we actually have this equation. Well, this equation is actually not the correct one, so let me just correct it. Suppose this is a matrix, or suppose it is a vector. What is the dimension of this vector? Well, by analyzing the dimension of y, we can easily find that this has a dimension of m cross 1, and here we were considering xj. But as we have written our matrix of features in a very special way, in this way we can actually use the whole matrix here to compute the gradients. Well, how can you use it? Suppose I am taking the transpose of this thing, and I am finding the dot product with my whole matrix. And what is the dimension of our matrix? Well, the dimension of x is just m cross 3. So after transposing, this will become 1 cross m, and we have m cross 3. So the answer we will be getting will be a matrix that will contain the dimension of which will be 1 cross 3. Well, this is gonna be our gradients for 3 weights. So let me just go back to our code section. So that is what has happened here, and obviously there is a minus sign. So this function is returning the g. Remember that it contains 3 elements. So now let me just run this portion again. And now here comes the most interesting part of our code. This is the stochastic gradient descent actually happening. Now we have defined a function, and the inputs are w new, the weights new, weights priv, learning rate, batch size, and number of epochs. And at first we are shuffling our training examples, and then we are entering a for loop for each epoch. Now here I am defining a empty list epoch loss. Remember, this contains the loss after completion of average loss after completion of one epoch, not after completion of one step. So after that we are again doing this shuffling. Because why we are doing this shuffling? Because we don't want to give a sequence, we don't want to provide the examples in a particular sequence to our algorithm. It may get stuck in some local minima. Okay, so after that we are iterating for each batch. Remember, the w new is the value calculated after the last epoch, and at the beginning obviously w prev and w new are same. After that I'm just appending the loss to our epoch loss, and after that I'm calculating the gradients by this function, and this is the simultaneous update step of our gradient descent algorithm. And see how easily we can do this step, just because we have uh, structured our data in a very particular way. And after that I'm just printing the loss after every epoch, and this whole function will return the last updated weight. So let me just run this function. And here is an important thing, that we are gonna initialize our weights and bias. Well, as our bias term is included in the vector of weight, so I'm just initializing this as randomly. Okay, now here you can see that size is x dot shape 1 comma, and that's it. Well, this will give me one numpy rank 1 array. So I am using this here because that will help me in this step, because this function also produces a rank 1 array, and that will also help me while doing this one. Okay, so for the ease of coding I am just using this type of arrays. So let me just run this code, and you can see that the shape is something mysterious. It is a flexible data structure, in a sense that the second dimension is actually flexible, so this can be used easily as a column vector, as a row vector. So that's what I am using here. After that I'm just gonna train my model. So here I am inputting both the w new and w prev as w, and my learning rate is 0.009. My batch size is 32, as I have mentioned earlier, and the number of epochs I'm gonna do here is 200. So let me just run it, and look at this. This is my first random weights, and this is my first ever calculated cost. And obviously you can see that, well, here's the noise I was talking about. 5 4 again 5. If it was a vanilla gradient descent, then it won't be like that, that would always decrease. But as it is stochastic gradient descent, there will be noise, but eventually I will achieve one minimum, and that will be very fast, and that will be in a less amount of time than vanilla gradient descent. So this is my final weights that my algorithm has produced. Now I'm just gonna grab the results. Well, this is the final portion of this code, and after seeing the result, we can have a deep breath. So let me just run it. Well, look at this, how beautifully the line has fit our dataset. So I hope that this video was very informative to you and your concept about stochastic gradient descent and mini batch gradient descent are very clear now. So if you have liked the video, please share the video, comment below, and don't forget to subscribe to Normalized Nerd. Thanks for watching.